right. Hello, everyone. Welcome to the LChem 1 week review. This is week 2. Right. So let me share my screen and we'll get started. Okay. All right. So just an introduction to this week's weekly review. Last week we covered, we had a little introduction about, the weekly reviews, about me, about the Student Success Center, about organic chemistry as a subject and as a course here at UTD. And then after all that, we got into the content, which is we start off with octet rule and formal charge, a little review from Gen Chem. Now we also talked about molecular formula and how to turn that into a Lewis structure, and then how to go from a Lewis structure to a line angle drawing. Okay. And then finally, we finished off with periodic table trends. I went over the acronym BEAN, which stands for basicity, electronegativity, acidity, and nucleophilicity. The nucleophilicity part you don't have to necessarily worry about until next unit, but basicity, electronegativity, and acidity will definitely be helpful. And if you want a review of all those topics, please go on to YouTube and just search up UTD peer tutoring, and you should find the course, the video, and the date that was covered last week. All right. So thank you for tuning in this week, whether you're in person, live viewing it, or recording on YouTube. Happy you guys are here. So this week we will be completing all the topics we haven't gone through yet, such as hybridization, functional groups, sigma and pi bonds, resonance. We'll talk about what a major and a minor contributor are. We'll talk about acidity and basicity, and another acronym that's helpful to know, which is ARYO. And then if you have time, we'll talk about alkanes, isomers, nomenclature. We'll review functional groups again when we talk about IR. But other than that, anything that we don't cover will go on next week, which I will talk about at the end of the session. Okay? Does anyone have any questions? If you have questions at all, feel free to just type it in the chat, ask me in person. Obviously, you can't ask me when you're recording or watching the recording. So if you do want to ask me questions, join one of the live sessions. All right? So if you have a question, if you need to interrupt me at any point, just let me know. Okay, with that out of the way, we will go to our topics for today. Okay, so we're going to continue chapter 2, which is going to involve hybridization, functional groups, sigma and pi bonds, resonance, and acidity and basicity. That will be the bulk of what we cover during this week's session. And if we have time, we'll see what else we can take a look at. All right, so this is week 3 of courses. So you had roughly about 5 lectures. Okay, so within 5 lectures, hopefully all of this should be a review. Regardless of what professor you're in, regardless of the pace they're going, I would hope all of you are going to lectures and paying attention. And if something's not clicking, you're in the right place. Okay. All right. So let's get started with hybridization. Okay. So hybridization is a concept from general chemistry 1 or 2. I forgot which one. But basically, it involves the S, the P, those orbitals. But we don't necessarily talk about D or F in this in organic chemistry. So we're mainly dealing with S and P, and specifically, is it sp2, sp, or sp3? Okay. And a little side note that you should remember, and I would hope you write this down somewhere in your notes. Anytime you identify the hybridization of an atom, make sure you always consider, can it resonate? Does it have a lone pair that can resonate? If it does, go with the lowest hybridization form. If an atom has a lone pair that can resonate and the atom turns from a sp3 to an sp2 molecule, then go with sp2. If an atom goes from an sp2 hybridization to an sp3 due to hybridization, stick with sp2. When I mean consider resonance, I don't mean always go with the resonated form of the hybridization. Go with the lowest energy and lowest hybridized form, which is obviously going to be sp2 when it comes between sp2 and sp3. All right, we'll talk more about that with an example with amide. Hopefully you guys have seen that example over and over again, because that is one of the most important examples to teach this topic. All right, so like I was talking about SP, SP2, and SP3, we are going to go over the electron domains, the bond angle, what it looks like, and all in examples. Yeah. All right. So again, these are the most important ones. So SP has 2 bond domains or electron domains, which means it has 2 sources of electrons connecting to that atom. Okay, and this should make sense already, and if not, we'll see an example and we'll go over what that means. sp2 has 3 sources of electron domains, and sp3 has 4 sources of electron domains. Okay, now bond angle, hopefully again this should be a review. sp has a 180-degree bond angle. sp2 has a 120 bond angle, and sp3 has a 109.5 bond angle. Okay? So, again, hopefully this is all making sense. If not, I would go back and review some general chemistry concepts. Okay? Now, to see an example, we have a R group bonded to carbon, which is triple bonded to nitrogen, which has a lone pair. Okay? So in this scenario, we would say the carbon has a sp hybridization, and we would also say nitrogen is sp hybridized. Okay? Because carbon has a bond here and 3 bonds here, but essentially 2 sources of electrons, a single and a triple here. It doesn't matter if it's a triple, it's the same domain, right? And same with the lone pair on nitrogen. This is one domain, this is one domain. Okay, so 2 sources of domains. You would have an sp hybridization, and this would be 180 degrees. Okay, I'm gonna speed it up because hopefully this should be a review. So we have a carbon there, R group there, R group there, and then a carbonyl on top. Okay, this carbon is sp2 because it has 1, 2, 3 electron domains. Okay, now let's go to sp3, which is going to be an example of methane, which is CH4. Okay, so as you can see, carbon is bonded to 4 electron domains. All right, it's as simple as that. That is most of what you need to know for hybridization, and you should be able to apply that knowledge to any atom and identify if it's sp, sp2, or sp3. You won't get into sp3 d1 or sp2 d2 or any of those. Okay. So now we'll talk about that special case that I was talking about. Okay. Looks like it doesn't zoom out any more than that. Okay. So we'll talk about this for now. Okay. So I want to know the hybridization of nitrogen, the orbital the lone pair is in, and the bond angle. That's what this symbol is. The angle between carbon, nitrogen, and the lone pair attached to nitrogen. Okay? All right, so the first question is, what is the hybridization of nitrogen? Okay. So at first glance, you could see that there's 3 bonds, 2 hydrogen, 1 carbon, and then 1 lone pair. So that would mean 4 electron domains, which would mean sp3, right? But remember that special rule, you have to always consider resonance. If nitrogen has a lone pair that can resonate, we have to consider what it's resonating into. Okay. And hopefully, we'll talk about resonance later, but hopefully you guys understand why this can resonate. But I'll go over it real quick. This lone pair can resonate with this double bond. So when I draw that, this is going to go, it's going to create a new double bond there, and this existing double bond will go on to oxygen. Okay. So when we redraw it, we have a new double bond there. Our nitrogen is still there. Our bonded 8 hydrogens are still there. We have a single bond there with, that looks like that. And we have a negative charge there, and we have a positive charge here. Okay? So obviously, resonating that lone pair does make the structure less stable, but we are only talking about hybridization. And in hybridization, this is sp3, but this, because it lost its lone pair and it turned into a double bond, whether it's a single bond or a double bond, it's still 1 electron domain. Okay, so it's going to be sp2 now. All right, so real quick, let's also take a look at oxygen. Okay, oxygen in its current form is sp2, but now it turned into sp3. Okay, but we're going to accept this answer and this answer. Okay, because those are the lower energy forms, lower hybridization forms. Okay. All right, so that should help us answer the first question. Hybridization of nitrogen is going to be sp2. Okay. Any questions about that? All right. If there's no questions, I will go on to the next question, which is what orbital is the lone pair in? Okay, and again, I'm talking about the lone pair of nitrogen. So this lone pair is resonating, right? Any lone pair that can resonate is delocalized, as in it is freely able to move between multiple places, whether that's 2 or 25. It's existing in different places, okay? Because it's existing in different places, we call that delocalized, okay? And any delocalized lone pair is typically going to be in unhybridized p orbital, okay? And I will draw what I mean if I can find some space, maybe in this little corner. Okay, so let me do that. Okay, so here is our nitrogen. Okay, here's our hydrogen, and then our carbon. Okay. Now, so the carbon, hydrogen are on a equatorial plane. Okay, and that equatorial plane is an sp2 hybridization. And again, sp2 creates a 120 degrees from each of these. So these are at equal lengths from each other, okay? Which is not the important part, but just so you guys can visualize a little bit better. So imagine hold your pencil or pen. Okay, imagine nitrogen is at the center. Imagine nitrogen is that pen. Okay, and imagine if you attached 3 feathers to that pen equatorially with 120 degrees apart. Okay. Now imagine if you added a p orbital, and if you remember from general chemistry, p orbitals are dumbbell-looking shapes which go up and down on the vertical axis or the y-axis, okay? So going back to our pen metaphor, if nitrogen is your pen, and if you attach 3 120 degree separate feathers, now imagine you're adding 2 balloons to the top and bottom of the nitrogen, okay? But inside the top balloon, you insert 2 marbles, if that's possible, or 2 tiny balls, okay? So these 2 marbles are at the top, and that is your lone pair. That lone pair exists in that unhybridized p orbital. It's called unhybridized because that p orbital isn't complete. Only the top is complete, but the bottom is still empty, right? So in this, well, we can actually answer question number 2, which is asking the lone pair the orbital is in, okay? And your answer would be the p orbital, okay? Let me know if there's any questions. Okay, I don't see any questions, so I'm going to move on. All right, so now the tricky part, and I kind of already explained the answer to this next question, but the tricky part is visualizing the bond angle between carbon 1, nitrogen 1, and the lone pair, okay? So let's go back to our pen metaphor, okay? So imagine nitrogen as a pen. Imagine carbon is at the end of one of the feathers attached to your pen. So the angle between carbon to nitrogen should be just 180 degrees, right? Or it should be flat. The bond between, or the angle between nitrogen and a balloon on top should also be 180 degrees, okay? Because it's just on the plane. So if carbon 1 and nitrogen 1 are on the x-axis, okay, and Nitrogen 1 and the lone pair are on the same y-axis. Now imagine the angle between all 3 points. Carbon on the feather, nitrogen on the pen, and then the lone pair on top of the pen, above the pen, the balloon. Okay, so that will create. It's kind of hard to see here, but it actually creates a 90-degree angle. Okay. I hope that made a little bit of sense. If it didn't make complete sense, I understand. This is a very difficult concept, especially to visualize. It's much easier explaining with my hands, and I'm not, the camera is very tiny. I'm not sure if you guys saw what I was doing. But hopefully it made a little bit of sense to understand why that is 90 degrees. If you understand a little bit of graphs of x-axis and y-axis, that should help with the understanding. And I would advise you to grab a pen and try to understand and visualize what I was talking about. So if you need to go back and re-listen to what I was saying, please do. But for now, we're going to move on. So the answer to this question, with this AMI, which is a functional group that we'll talk about, what is the hybridization of nitrogen? It's going to be sp2 because it can resonate. What is the orbital of the lone pair? It's going to be the p orbital because the lone pair is delocalized and it can resonate and move around. And what is the angle between carbon, nitrogen, and the lone pair? And again, it's going to be 90 degrees because the p orbital is sitting on top of your nitrogen atom, and the carbon is equatorial on a horizontal plane, while the p orbital is on the vertical plane. Okay. All right. I'm going to quickly check if there's any questions. Okay, no questions. So hopefully this is making sense. I'm going to move on. So now we're done with hybridization. That is pretty much all you need to know. Of course, I would suggest practicing with any compound really. You can identify the hybridization as long as there's a organic chemistry molecule involved. Now we'll talk about functional groups. All right. So there is about maybe 12, 14 functional groups that you should know. I'm gonna zoom out a little bit. Okay, get the black marker. So I'm gonna draw the functional groups and then we'll label them. Okay. Actually, that's fine. Can I draw? Oh, perfect. Okay. It's always a struggle to draw a benzene ring. All right. Oh, that's too much. Okay, so as I'm doing this, I would suggest you guys also draw along with me. just a couple more. There's no space. All right. Okay. All right. We are good. Anyone have any questions? Okay. All right. So let's go by all of this. And as you can see, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And I guarantee you this is not the full list, but this is pretty much most of what you need to know, if not all, for OCHEM 1. OCHEM 2, there might be a little bit more, but for now, this is it. Okay? So a single bond is called alkane. A double bond is called alkene. And let me zoom in, maybe I can write a little bit better. So erase those. Alkane, alkene with the E, and alkyne with the Y. Okay, so if you notice, they're all the same except the ending, which is the A, E, I, or Y ending. Okay, but that's your triple, single, a single, double, triple bond. Now let's go to the next one, which is alcohol. Okay, so OH is your alcohol group, SH is your thiol group, and if you notice, it has, oh, forgot to do it in blue, alcohol, thiol. Okay, so it has the OL ending, and that should be not a T, an L. Okay, it has the OL ending. Okay, now X, take a guess what it means before I read it. And if you guessed halogen, you are perfectly correct. Any X represents any of the halogens, which is fluorine, chlorine, bromine, iodine. Those are the major four. Okay, and I would hope to God you guys know what this means. It's a benzene ring. The most common organic chemistry compound, not necessarily used in OCHEM, but like recognizable that people associate OCHEM to. Okay, so this is a benzene or a benzene ring, whatever you prefer. All right, so moving on to the bottom row, we have, so this is just the carbon double bonded to a oxygen, and that is called a carbonyl. Okay, now we have a carbon, we have the carbonyl, but we also have two methyl groups. And remember, methyl is a carbon with 3 hydrogens. Okay, so this is called a ketone. This is called a aldehyde. So the same thing, but on one of the sides we have a hydrogen. This is called a formaldehyde. Make sure I get the spelling correctly. Okay, so similar to aldehyde, but it has an extra hydrogen. Let me scoot over here. Oh, okay. Now, the one with the alcohol attached to the carbonyl is going to be called a oh, it might have froze on me. Let me refresh real quick. So don't need that. Let's go to draw. Let's see if anything messed up. Okay, looks like all this random stuff. So let's go to erase. Okay. All right, so let's zoom in again. Okay, that's not working. Sorry about this. Okay, so this is a carboxylic acid. Okay. This next one is called a acid chloride. Chloride because it has chlorine on it. Okay. Now the NH2 with the carbonyl is going to be called a amide. This is the functional group we used for hybridization earlier. Now just a NH2 by itself is called an amine, a name that should also be recognizable. Now this group is called ester, E-S-T-E-R, and this group without the carbonyl is called ether. Okay? So if you notice, most of these have the carbonyl group, which is the C double bonded O. Okay? So ketone, aldehyde, formaldehyde, carboxylic acid, acid chloride, amide, and ester are all going to be under this carbonyl family, if you'll have it. Okay? Formaldehyde and acid chloride are less popular and less seen. You might see a little bit more in OCHEM 2. So ketone and aldehyde are the most famous ones, and of course carboxylic acid, and then amide and ester are also there. Okay, and then besides those, you also have ether and amine. And if you notice ether and ester, there's a chance you might get that mixed up. So just remember the difference. Okay. All right. So moving on to sigma and pi bonds. So I want you guys to take a minute and tell me, and tell me how many sigma bonds this molecule has and how many pi bonds this molecule has. Okay. Obviously, pi bonds are going to be a little bit easier because they're easier to spot out. Sigma, you'll have to do a lot more counting. So just take a couple of seconds, or not a couple of seconds, but take a minute or two and try it on your own before I give out the answer. Okay, hopefully you started with the pi bond because it's the easiest to spot out, but there should be 6 pi bonds. Okay, and the 6 are coming from 1. Each double bond is 1 pi bond, and each triple bond is 2 pi bond. Okay, so I see 1, 2, 3, 4 double bonds, so that's 4 pi bonds. And then there are 2 pi bonds in this triple bond. So 4 plus 2 equals 6. So that's why we got 6. Now sigma bonds are going to be a little bit tricky, and I haven't done this, so I'm going to do it with you guys. So remember to count your hydrogen bonds. Remember in organic chemistry, carbons and hydrogens are not shown. Hydrogens will be shown if they are bonded to an atom other than carbon. Okay, so we are missing some hydrogens. All right, now your structure is complete. And of course, the lone pairs are also not shown, but lone pairs don't affect sigma and pi bonds, okay? Because they're bonds. Okay, so we'll just go around this way. So hydrogen, maybe I'll do it in green. I'll just place a dot everywhere there's a, and remember sigma bonds, it doesn't matter if they're single, it doesn't matter if they're double, or if they're triple. They all count as 1, okay? And this might seem basic, but it could lead to, there's a chance of error is what I'm saying. So each of the hydrogens, so just gonna place a dot so I don't forget, and I'll get to something else later, and then each of the carbon-carbon bonds get a dot. So there's another dot here, carbon to oxygen, there's a bond there, carbon to carbon bond, carbon to oxygen bond, carbon to carbon bond, and carbon to carbon bond. Now there's one thing we are forgetting, which is the oxygen to hydrogen. There is also a bond there. Okay, now just count up all the dots. Let's see, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so you should have gotten 20 unless I missed something, and that's completely on me. But there should be 20. Okay, and if you didn't get that, and like I said, I could be the one at fault, so feel free to correct me. And if you didn't get that, maybe try recounting, and if you're getting 20 on the second or third try, that means you might have forgotten one of the bonds. Okay? All right. So let's just recap everything that we've gone over. It looks like I can't zoom out for some reason. Okay. So we're pretty much more than halfway done. It's about 1:42. So we talked about hybridization. So if you're viewing it online, whether it's live or recording, and you want screenshots, so you can take better notes, or so you can keep it for yourself and view it later. That's up to you. So I'm just gonna quickly, slowly scroll through everything that I've done so far before I move on. Okay. So this is hybridization. This is the special case. Here is all the functional groups. And here is the sigma and pi bond example that we did. And now we're going to talk about our favorite topic, resonance. Yay, resonance. All right. So trying to zoom in, but it won't let me. Sorry, bear with me for 1 second. Can I scroll? Oh, I can scroll. Okay, perfect. All right. So whenever I teach resonance, I always start out with 3 carbons. Okay, this should be your most basic resonance example. So we have 3 carbons. Carbon 1 has a negative charge. Okay? Carbon 1 can also have a positive charge. And carbon 1 can also have a radical. Okay? Regardless of what kind of charge, they all work the same. Okay? Now, this charge is going to come here. Okay? And that will force this double bond to go to this atom. Okay? Which is why in our resonated form, we have the charge on carbon 3, whether it's a negative, positive, or a radical. Okay? Also, these words have names on it. Okay? So again, this is negative, positive, and radical, right? But the negative and positive also have a organic chemistry term to it. This is called a carboanion and a carbocation. Okay, so this term, cation and anion, should be a familiar term from general chemistry. The only new part is the carbo part, and obviously that stands for carbon. Okay, so it's an anion or a negative charge on a carbon. It's a cation or a positive charge on a carbon. Okay, so know what those words mean and get used to that terminology. So a carboanion and a carbocation. Okay, so obviously I'm not going to say that all the time. I'm just going to use negative or positive, just some side information that may come into handy for the future. Also, notice how I did my arrows, okay? So a charge will only travel through atom to bond to atom to bond, okay? It will only go this way. It will not go this way, or, okay? So this is the wrong way, and this is the right way, okay? Think of it as a train track, okay? When you're, I mean, I don't know why you would do this. Let's say you're walking on top of the train. You have to walk, or the train goes on the tracks in a straight line, right? The train cannot jump. I mean, it's physically not possible. I mean, who knows, maybe in the future, but for now, with our technology, it's not possible. Okay? So think of it as a train track. If it helps you, if it doesn't, ignore me. I don't know what I'm talking about. All right, so the point is resonance. You have a charge. That charge can move around the atom if it has a double bond. Okay, remember a double bond is nothing but, or a bond is nothing but two electrons. Okay, I might have talked about this last week. Okay, a bond is two electrons. Okay. And as long resonance can occur as long as a charge is bonded to a carbon that contains a double bond. Okay, so it has to be one carbon away. This cannot resonate. Okay, if you have a charge directly on top of the double bond, whether that's a negative, a positive, or a radical, none of those can resonate with this double bond. Okay? Likewise, let's say you have a, oh, that looks ugly. I'm sorry if this is tiny. It looks big on my screen. Let's say you have a negative charge there and you have a double bond all the way over here. Can it resonate? Absolutely not. It is way too far away. It can't go all the way here, as shown above. Okay? It needs to be right next to each other. Okay, I don't know why I just did that. Control. Okay. Yeah, so this cannot happen. Okay? This cannot happen. It can only happen when you have this 1-3 model. Okay? And by 1-3, I mean the charge on carbon 1 and a charge and a double bond on carbons 2 and 3. Okay? So, and if you didn't know already, this is the resonance symbol to showcase between two compounds. And we already talked about when resonance can occur and how resonance can occur through these arrows. Make sure you are showing the arrows, especially when you're starting out. It will really help you, I guarantee you. And make sure you are also numbering your carbons or atoms. Okay, it will also really help you. Okay. If I didn't show 1, 2, and 3, and 1, 2, and 3 here, it would have been slightly harder to understand what's going on. Okay? All right. I mean, this is most of my viewers are going to be watching this on YouTube, so I can't it's difficult to understand if you guys are understanding this concept. So I highly recommend, even if you are completely understanding it, to try out coming in person or live, just so there's better engagement between both me and you. So for me, I can understand what areas you need help with and what areas you're comfortable with, and we can just move on. Okay, if not, I will have to assess the pace by myself and understand how I feel. Okay. All right. I would recommend you guys do lots of practice problems on resonance. This is the core concepts of the beginning of your organic chemistry foundational knowledge. Okay. Understanding hybridization and resonance is very important into understanding everything else. Okay. This knowledge will build on top. Okay. All right, now we have about 20-ish minutes. We're going to talk about acidity. Okay. Now, acidity is a topic you will know until you will have to apply until the final exam of OChem 2 even. Okay. It will appear on every single unit exam. It is that important. And luckily, you will learn it in the next 20 minutes. And you should be able to apply that same knowledge even until the end of, all the way up until May. Of course, there's going to be additional components to acidity, and you'll add on top of that knowledge. But for the next 20 minutes, you will learn everything there is to about, well, not everything, but you'll have a lot of knowledge and hopefully confidence after this. Okay, and my favorite way to teach acidity is through a practice problem. And give me 1 second to bring that out. Okay. All right. So I'm going to draw. So acidity, base acidity, and other concepts are tested through a ranking format. And this ranking format is something that is kind of unique to organic chemistry. I mean, ranking is common in a lot of subjects, but in between general chemistry, organic chemistry, and biochemistry, organic chemistry uses ranking as a test format question for quizzes and exams and final exams. Okay? And of course, there is no partial points in ranking. And of course, there's no partial points in multiple choice. I'm not quite sure if your exams are multiple choice or free response, or a little bit of mix of both, or matching, etc. Regardless, knowledge can be applied in any form, and depending on the format, there could be test strategies that you can implement. And if you have questions about what should I do if it's multiple choice versus what should I do if it's free response, feel free to come and talk to me. All right, so in OChem, ranking should have 5 compounds, and there's going to be a question, which one rank based on stability, rank based on acidity, rank based on highest energy, etc. Probably should not make that super big. Let's see. Okay. So there's the first one. There's the second one. Feet are getting tired. So real quick, I hope you guys can hear me. Okay, the microphone's on. I got a little bit paranoid that there was no audio this entire time. That would have been sad. So next question. All right, so for the basis of teaching, I'm actually going to have 6 compounds. But ideally, or typically, you shouldn't have more than 5. Okay, so we have 6 compounds. Okay? Now we are going to talk about our new acronym called ARYO. A-R-I-O. Okay? ARYO stands for atom. R stands for resonance. I'm just going to abbreviate it. Res means resonance. I stands for inductive effects. And O, you guessed it, stands for orbital. Good job. All right. So when I'm talking about atom, I'm talking about the size of atom containing the charge. Okay. All right. So whenever you're ranking 5 compounds based on acidity, these are 5 acids, right? You have to turn them into 5 conjugate bases. Okay. And how do you turn an acid into a base? That's right. You have to donate that proton away. So that acid will then gain a negative or a positive charge. Which one? Yep, it's going to be a negative. Oh, you guys are really good. So the first step is going to be removing the most acidic proton. Okay? That proton is not always right here. Okay? It could be elsewhere. Okay? So just going to place a negative charge on all of these. Okay, now going back to our definitions. So resonance doesn't need a definition, but I will say more res is better than less resonance. Some of these compounds can have multiple resonance structures. The more resonance you have, the better stability and better acidity, acidic compound it is. Something I forgot to mention about acidity, resonance as a concept, resonance is good for stabilizing a charge because that charge will be spread throughout the molecule. Okay, so let's actually go back real quick, and I'll explain what I mean. Okay, so remember how I had this 1, 2, 3 atom, and remember how I had that double bond? So that charge existed both on carbon 1 and carbon 3, depending on which resonance form I did, right? So that negative charge, or that double bond, is basically exists both between carbon 1 and 2, and both between carbons 2 and 3. Okay? So this negative charge that was once concentrated on one single atom has now been spread across 3 separate or connecting atoms. Okay, so when you have a concentrated imbalance of charge and you spread it across, you spread it thin and you increase the surface area of that charge, you are diminishing its value, and that instability decreases tremendously. And that is only with one double bond resonance. Now, if you have multiple resonance and it's spread across an entire larger surface area, then that negative charge is very, very tiny, okay? As opposed to a very large negative charge right there, okay? All right, hopefully that made sense. Okay, moving on. So more resonance is better. Now, inductive effects, whenever we talk about inductive effects, we are talking about halogens. I know that's kind of hard to read, but that stands for halogens. And within halogens, there are 2 concepts. Okay? First thing, the stronger the halogen, before I get into this, halogens equal magnets. Okay? At least in my world. and you are learning organic chemistry in my world. You're in a good place. I'll take care of you. All right. All right. We got about 15 more minutes before I wrap it up. All right. So think of halogens as magnets. Okay. The stronger your halogen is, the stronger the magnets. Okay. What is the strongest halogen? And halogens have to do with electronegativity, right? A little bit. Yeah, that's right. It's fluorine. Okay, so fluorine is going to be the strongest halogen. It's going to be the strongest magnets. Okay, so halogens have electronegative or high in electronegativity, right? So if those halogens are going to want that extra electron, right? Just like how oxygen prefers to have a negative charge compared to a carbon, halogens want that much more, because halogens have 7 valence electrons, and they want that extra electron, right? So they don't care or if they have more electrons. They're gonna pull and be selfish, okay? So just like a magnet, they're going to attract extra imbalance of electrons. So when there's a negative charge across the compound and they're on one side, on the other side, they're going to attract that negative charge like a magnet. And in theory, just like how resonance spreads that negative charge, halogens have the same concept by pulling that negative charge across the compound and spreading it thinner. Okay? So if you have a fluorine, that is much better than a chlorine, which is much better than a bromine, which is much better than an iodine. Okay? So size, well, not size, because iodine is the biggest size, but electronegativity and the strength of the halogen matters, as well as the location. So of course, if I have a magnet across the room versus if I have a magnet right next to the negative charge, the magnet right next to the negative charge is going to have a stronger effect. Let me see if I'm getting that backwards. No, that's right. So actually, let me make this change. Okay. All right, so going back to our concept of inductive effect, this is one of my favorite topics, or ARYO is one of my favorite topics. All of OChem 2 is my favorite topic, but next semester. So inductive effects, think about halogens. Halogens, think about magnets, and in terms of halogens and magnets, think about two different concepts. That's the strength of your halogen. Fluorine is better than chlorine, chlorine is better than bromine, bromine is better than iodine. And then next, think about the location. How close is this magnet? If you have a magnet right next to the charge's face, it's going to be more impactful than if it's across the room, right? And notice, halogens want negative charges. So this only applies to carboanions. If they are pulling carbocations, they are making an atom that is lacking electrons much worse. They are pulling whatever electrons it already has and making it worse. So inductive effect has a positive effect on negative charges and a negative effect on positive charges, which has, a reverse or inversal effect on positive charges, however what you want to think about it. All right, and orbital just means sp is greater than sp2, which is greater than sp3, okay? So this isn't used as much, but basically the greater your sp character, S character there is, the greater the acidity and stability is, okay? Which means, remember, triple bonds are kind of associated with sp, double is considered associated with sp2, and single is associated with a sp3, okay? So let me quickly draw that. Okay. All right, so now that we kind of identified what ARYO stands for, we'll go through each of the 5 compounds and we'll talk about them, okay? And I know this is a very long concept. This might be boring. I hope it's not boring. It's a concept that will be timeless, okay? What you put into learning and understanding this will really benefit you and help your grade and your knowledge for OChem. Okay, so I appreciate you guys sticking with me. I'm sorry if I'm kind of mumbling or yeah. All right, so one more thing before I move on. Even though ARYO is in this order, resonance is actually more important than the size of the atom that contains the negative charge or the charge, okay? So resonance is the most important factor, okay? And then it's the atom, and then it's inductive effect, and then it's orbital, okay? Resonance, atom, inductive effects, orbital, okay? So how we do this checklist, and that's what ARYO is, it's a checklist, is we're going to go through each of the atom, each of the concepts, and we'll write it down, okay? So by atom, I'm just going to put O negative, S negative, O negative, O negative, O negative, O negative, okay? So if you remember our periodic table trend, atom is on the bottom right corner. It's inverted, so it's on this side. So as you go down the periodic table and as you go to the right of the periodic table, your acidity increases. And if you remember the relationship between oxygen and sulfur, sulfur is directly one row underneath oxygen, which means it is a bigger size. It has more valence electron shells. Sorry, valence electrons are the same, but basically has more rings, right? So the size of sulfur is much larger, and the same concept of a negative charge being spread throughout a larger atom is much more stable and much more acidic than a smaller atom being concentrated. So just comparing oxygen versus sulfur negative is much, much better. Okay, so we'll keep that in mind, but we won't make any sudden moves, okay? Now, for resonance, all we're going to do is put a X or a check mark. X if it doesn't have resonance, check mark if it does. If it does, it is automatically better than everything else that isn't. So, again, forgive me for the slight angle of this, but this is for the first one. I don't see any double bonds, so no resonance. The middle one, this is a carboxylic acid, if you guys remember back from the functional groups. This one does have a resonance, and the rest of them do not. Hopefully, you guys are able to understand which one has resonance and which ones don't. Okay, because there is only one compound that has resonance, this is automatically going to be number 1. This is the most acidic compound out of these 6 compounds. Next up, we have 5 X's, right? Remember, after resonance, we have to look at atom, okay? We have 5 compounds that don't have resonance, and 5 compounds, 4 of them are oxygen, and 1 of them is sulfur. And we determined that sulfur is a larger size, larger atom, which can handle that negative charge better. So the one with sulfur is going to be our number 2. And if you look at the rest of the molecules, they are all O negative, X, O negative, X, and etc. Okay? This is where inductive effect comes into play. Okay? So for this part, we are going to say if it has inductive effects. So the first one does not, so we'll put next. We don't need to worry about compounds 2 and 3 because we already assigned or ranked them. So let's look at compounds 4, 5, and 6. So compounds 4 has a fluorine, 5 has a fluorine, 6 has a chlorine. Okay? So the strength of the halogen matters more than the location. Okay? But in this case, we don't even need to worry about that. The fluorines are going to be automatically much better. And if something doesn't have inductive effects, remember, inductive effect is a good thing. It will increase your acidity or stability for negative charges, which is what acidity should always be. Acidity is always associated with negative charges because you are giving away a proton. And basicity is associated with positive charges because you are receiving a proton. Okay? So that being said, if between the 4, 3 of them have inductive effect, which helps acidity, and 1 of them don't, the first compound is going to be our number 6. And then also, if out of the 3, 2 of them are fluorine, which are automatically better than chlorine, the chlorine one is going to be our number 5. So we're not using much thinking. We're just using basic understanding of how rankings work and how ARYO works. Now, between my 2 fluorines, what is the difference? That's what you have to ask between any ranking question. What is the difference between this compound and this compound? Are there different atoms? Do they change the location of it? And in this scenario, they change the location of where that fluorine is attached. Okay? Also, it is about 2:16, so I'm going to wrap it up. Okay? So the 4th compound, fluorine, is closer to the negative charge than the 5th fluorine. So this is going to be our number 3, and this is going to be our number 4. And if you want to, check yourself about the other rankings, you can see that 4 and 5, because they're right next to each other, the halogen is in the same location, but the fluorine is stronger. It's a stronger magnet. Okay, that's why this is number 4. Chlorine is number 5. This is number 6 because it doesn't have any halogen additional upgrades, if you will. Okay. And orbital, we didn't even need to worry about because within resonance, atom, and inductive effect, we were able to distinguish which one is number 1 and which one is number 6 and everything in between. Okay? So this is an acidity ranking problem that I explained ARYO, the acronym. I explained how resonance and atom and inductive effect and orbital all affect the acidity of a compound. Okay? I also explained how you have to remove the most acidic hydrogen at the very beginning. And I also explained, I walked you guys through the entire problem. Okay, so if you guys ever need a refresher before your quiz or before your exam, please come back to this recording on YouTube. Just search up UTD Peer Tutoring and just go to the specific video. Come to this lesson, review everything I said, okay? All right, so I'm gonna wrap it up. And I know we didn't talk about basicity. It's slightly different, but in theory, if you want to rank a basicity problem by acidity and then flip everything, you could technically do that, I believe. And if I'm wrong, correct me, someone. All right, so besides acidity, we talked about resonance. So I'm going back if you guys need to take screenshots of anything. And I apologize if it's too small on the screen. I tried my best with zooming in and out. So there's the acidity one if you want to screenshot that or write it in your notes. Here's the resonance one. Here's the sigma and pi, function groups, the special case of amide and hybridization. Okay. All right. So we talked about everything I wanted to. Obviously, we didn't get to chapter 3. I mean, we kind of already talked about function groups. But we will take all of this. Oh. We're going to take all of this and we will put it to next week. All right. Okay, and if at any point you guys have any questions, feel free to come visit me during my peer tutoring shift hours. Again, we are located in the library, which is in front of the plinth, in the basement, the bottom floor, and it's this big room in the basement. It's really hard to miss. And it doesn't have to be me. It could be any of our tutors. All of our availability is posted online as well as on the windows of the peer tutoring lab. Okay? All right, I'll see you guys next week. Thanks for tuning in. Bye.